We are going to see in this tutorial the different types of boxes, and the ways to import fins into the software. We can import 3D files of fins. If we already have files nearby. First, small adjustment, we will pass the aspect of the board in phase shaped, to have the direction lines of the fins, and pass in wireframe to see by transparency. Here, we will go to the Fins tab and we will immediately import fins. We will start with an STL import, therefore of FCS Central Performer fins. And so to import, just use this function on the right and select an STL file. We have an import interface that opens. This interface recognizes the profiles that make up the fin, and also recognizes the outline. We see the fin behind. In STL, you can see its base here. And FCS2, and we see the profile recognition system. We are going to import this fin into our project. Here, we imported our Central Performer fin. When we bring a 3D geometry in STL in the software, we do not import the base, we only import the working surface that interests us. But we can then choose the type of base that we want to apply. I can select FCS, FCS2, Box, Future, Future 3/4, or nothing at all. So no matter what type of base we import, we can redefine it at will in the software. We will see that, after importing the STL fin, we can edit it to apply an image to it. And if it's a performer, we have an image of performer. We apply it and we can see it being applied on the outline. Another small detail during the import, we can detect profiles which are a bit different. And if you see at the base, we have a NACA0011 profile. In the middle, a NACA0009. And here, a NACA64. We have different types of profiles, depending on the height position of the fin. We can calculate the hydrodynamic performance of this fin. I can already now test its hydrodynamic performance, solo, i.e. just the wing alone. For example, here, at 6 meters per second, I have a drag of 1.4 newtons. If I increase the angle of attack, I see the drag and the lift of the aileron displayed here, at the speed of 6 meters per second. I could go to 4 meters per second so I can test the hydrodynamic performance with this solver. Here, we see the details of the solver, which makes it possible to calculate the performance of this profile in different speed situations. And this solver integrates the vortex losses at the ends. It is a fairly powerful tool based on the Prandtl lifting line theory, i.e. we will calculate and integrate the vortex losses relating to the fin length. So here we have a hydrodynamic analysis tool for an imported fin. So you could import any fin like this and test its performance. We apply and we close, and so we have our FCS fin here. Before the export, we could, for example, choose its case, here in FCS2, and we can export. So STL. To make a modified copy. On which we could apply new dimensions, or new profiles. So the STL export is done with the new base. And we can edit with the Desktop Explorer. There, I double click and I open with my Explorer. I have my 3D STL file that I could use to export to a 3D printer. So that's it for the STL export and the different types of enclosures. We're just going to look at a little thing at the level of the types of boxes. There is a difference between the FCS systems and the future system. FCS does not integrate a cant angle between the working surface and its type of base. It is the box in the board that generates the cant angle. This is not the case with Future, which integrates the cant angle in the fin between the working surface and the base. Let's see an import example. So I removed that fin there. We will import here a twin perf side fin. There. With cant angle detected on import. So the software detects the various profiles that make up this fin. We see here at the rear the imported fin, and we can see that here there is a future base, with an angle between the working surface and the base. We see that the fin is vertical, and at the bottom the face of the base is not vertical. The software will just stake out the working surface, without worrying about the base. But he detected the cant angle of 6 degrees. And when importing our future aileron, with its cant of 6 degrees, we can see that our working surface is at 6 degrees. If we display here the future base, we can see no vertical figure. Whereas if it is an FCS base and would be in the continuity of the cant angle generated by the box in the board, we also note that, in implanting this vertical fin, that it has a flat face, and a face with an extra dose. This shifts the layout a bit. In the header types area, we have a Y offset set option to align the case to the face to generate STL files with perfect strength and continuity. Here it is. This tutorial is complete.